to this video on a significance test for a mean. By the end of this video, you should be able to state and check the random 10% and normal large sample conditions for performing a significance test about a population mean. You should also be able to calculate the standardized test statistic and p-value for a test about population mean, and you should be able to perform a significance test about a population mean. So for today's scenario, we're wondering, are you getting enough sleep? So it is recommended that teenagers get 8 hours of sleep a night. Try not to laugh when I say that, but that's what they recommend. I do not believe my students are getting the recommended 8 hours of sleep tonight. So to test this, I took a random sample of 10 students from class and recorded the number of hours they slept for each of those people. Now, we're wanting to know, does the data provide convincing evidence that the AP Stat students get less than 8 hours of sleep per night? We're going to use alpha 0.05. All right, so for our sample, here's what I've got when I asked 10 people. So I got 6.5 hours, 4.75 hours, 5 hours, 8 hours, 7 hours, 7.25 hours, 4.5 hours, 5.5 hours, 7 hours, and 6 hours. So pause the video, put this into your list 1, and run one variable stats on them and come back to the video. Okay, when running these stats, I put in the 10 values. I got an X bar of 6.15. And then I got my sample standard deviation of 1.19. We'll round it to. All right, so I'm thinking we have less. That's what I'm concerned about. Our sample statistic shows us that we got 6.15 hours. So let's state an appropriate hypothesis for a significance test, and we're going to be sure to define our parameter of interest. So for our null, the null is the claim, meaning no difference than what's being claimed. Well, what they're saying is the mean needs to be 8 hours, because that's what the recommendation is. I think it's not 8 hours because when I took the sample, I got less. So we're going to have our mean for our alternate is going to be less than 8. Now, so before we used p here for proportion, but we're talking about population means here, so we want to use mu. And what does that particular mu mean? So we need to define our parameter. And so I always go back up and see, what is the question asking? Do these data provide convincing evidence that AP Stats, get less than 8 hours of sleep tonight? So I want to know the true mean hours of sleep. Okay, so we have true mean hours of sleep for my AP Stat students, because that's the only ones I'm talking about. Okay. Now we've defined our parameter. We've written our null and alternative hypothesis. Remember, when we write these, that null, we always assume it to be true. That's the only way to go through with this, and then we'll make a decision based off of if this is true, how unusual is our result. Okay, so our conditions that have to be met, there are same ones, random, 10%, normal. So random, it was a random sample of 10 students. Okay, then we have our 10%. I only talked to 10 students. That is less than 1/10 of all of my students, AP Stat students. Okay. Then normal. So remember, with normal, we need to look at, is the population normal? It doesn't say anything about that. Is my sample size big enough? No, it's not, because I only talked to 10 students. So that leaves us with the last choice of, we have to examine the graph. Okay, so I'm going to do a little quick little dot plot here. So we had 4, 5, 6, 7, 8, and then I kind of broke these into halves and quarters. There's a half, and then my quarters. Half, and then my quarters. Okay, so we could graph them. That should hit everything. So we had 6.5. So go ahead and finish your graph and come back when you're done. Okay, so in looking at our graph, we can try and draw a curve over it. There's no real strong skew or apparent outliers. So we're just going to make this, we'll just state that, no strong skew or outliers. So we're okay to continue. All right, so give the formulas for the mean and the standard deviation of the sampling distribution. So we're talking about means. We're talking about a one sample situation. So on the back of your formula sheet, that can help you. The mean of the sampling distribution is equal to the mean of the population, which is our null hypothesis. It's our claim, which is going to be 8. Then our standard deviation of our sampling distribution, well, it's be the standard deviation of the population divided by the square root of the sample size, except we don't have the population standard deviation, and you rarely do. So we're going to end up using the sample standard deviation, okay, divided by the square root of n. And so in this case, that is 1.19 divided by the square root of 10, which will equal 0.376. So that's going to be, and we don't, when you're using the sample standard deviation, we call that the standard error of the sampling distribution for X bar, because we took the sample standard deviation divided by the square root of n. Okay, so this is the sample standard deviation. The whole thing is the standard error. Now, let us draw a picture. So up until now, we have been, we'll just draw a curve, a nice symmetrical curve. Okay, we're wondering about right here, 8 is what the claim is. We got 6.15. So we're wanting, remember, you're always wondering how, that far or more extreme from the mean. How unusual is that? So we're looking for that area right there. This is not a normal curve. Okay, this is a t-distribution, because when we use our means, we have to use a t-distribution. So we can't write n and then the mean and the standard deviation, because this isn't normal. This is a t-distribution. So we're going to say this is a t-distribution with a degree of freedom that equals, well, I had 10 in the sample, and your degree of freedom is always 1 less, so instead of 10, we're going to write 9. Okay, so this is a t-distribution with a degree of freedom of 9. So the t-distribution to get your test statistic looks very, very similar from doing the z-score. It's the same formula, it's just where do some of the numbers come from, or where you look is going to look a little different. So instead of z, we're going to write t, or our test statistic. And our score of interest was the 6.15 that we got in our sample, minus the claim of 8, divided by that standard error that we got back over here, 0.376. And when I got that, I got negative 4.92. All right, So this can be done with technology, but every calculator is just a little different. So I'm going to show you on the table what will happen. So we need to use table B. We are going to go to our degree of freedom, which is 9. And we're going to go across. These are all our test statistics. We're going to get as close to 4.92 as we can get. This is negative 4.92, but because it's symmetrical, we're just going to look for the positive. The area will still be the same. The information will still be the same. So on 9, 4.92, 4.92, 4. Oh, it's all the way off to the side. It's out over here somewhere on the 9 level. Okay, so all the way out that way. And the numbers are getting bigger and bigger out here. But if we look up here, these are our tail probabilities. And notice how they are getting smaller and smaller and smaller as they go this way. So if I've gone off the chart to the right, my p-value is less than 0.0005. Okay, so let's take a look. So our p-value is less than 0.0005 because I don't know exactly what it is using the chart. If you use the calculator and your textbook walks you through how to do this, it's in the distributions, second vars to get your distributions, and it's a T for t-test CDF, cumulative, remember doing that. And our lower number is somewhere into negative infinity. My calculator populates that in for me. My upper number was what we got for our test statistic of negative 4.92. And then I tell it the degree of freedom of 9 because it needs to know where it should look. And when it calculates this for you, now you're not allowed to write this on the test. This is what you would want to do, is set it up this way. Set it up like we've always been doing. And I get 4.12 blah, 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 e to the negative 4. So what that means is the decimal is going to be 4 places to the left. So there's going to be 3 zeros. So by technology, we got a p-value that equaled 0.0004, which is less than 0.0005. So this is what we're able to tell from the table. But with technology, we were able to get a little bit closer number. So either is acceptable. Okay. Now, our conclusion. I want you to try to write this conclusion. It's the assuming the null is to be true, that whole conclusion. So give that a try and come back to see how you did. All right, so we've got our p-value by technology is all I've got written here right now. So assuming mu is 8 hours, that's our null, of sleep a night is true, there is a 0.0004 probability of getting the average of 6.15 hours of sleep or less purely by chance. So a very tiny chance of this happening. Because 0.0004 is less than 0.05, we reject the null. We do have convincing evidence that Dr. H's stats students have a mean sleep time of less than 8 hours of sleep a night. Okay, so you got to make sure you have context. We made our comparisons. We assumed our null was true. We rejected the null because our results were really kind of unusual. Okay, so this negative 4.92, that's your t-test statistic. Before we were finding a z-score, and this is like a t-score. Okay, we had our standard error, which is the standard deviation, sample standard deviation divided by the square root of n. And don't forget over here that your mean for your sampling distribution will always equal your null value. Because it's an unbiased estimator, and it should be telling you about where the center is. Okay, let's go ahead and flip this over and do the summary. All right, just a quick review on our conditions. You have random, and you're looking for a random sample or a random assignment. 10%, which you don't need if you have random assignment. Remember, your n is less than or equal to 1/10 of the population. And then your normal. There's the 3 things that to look out for, and this is the order you should always look for them. The first one, that's when you want to see first, if that's there, that the population is approximately normal. Okay? The population is approximately normal. If you do not see that, the second thing you want to see is you want to have a sample size greater than or equal to 30, because then you'll have central limit theorem will kick in. If you do not see that, your last option is to examine the data and say data shows no strong skew or outlier. And draw a quick graph. So for that guy, you've got to draw the graph. Now, here's the other thing. You are not going to be given a free response question that you cannot go forward on. If it's questionable, if you feel like it's a little skewed, you're going to do the work anyhow. So you would just mention, I see some skew, I'm going to go ahead and proceed with some caution. Like you're letting the reader know, I see it, but we're still going to do it. Don't leave anything blank on a free response question. They wouldn't be asking it if they didn't want you to do it. It'd be better to do it than leave it to blank. So when we do our t-test, you take the score of interest, which is your test statistic, minus the mean, which is your null, and divide it by the standard deviation of the sample, your standard error, divided by the square root of n. That will give you your test statistic. Okay, and then you'd have to go look on table B to see about it. Now, the numbers, you're not often going to find the exact t-score. So this is your test statistic. So if we're looking on here, say we had to do, we'll go back to a degree of freedom of 9, and say our test statistic fell between these two, it was somewhere between these two numbers, we would have to use both of these as our p-value. And then depending on what confidence level, you know, if we are like a 95%, our alpha level, alpha 0.05, it can be equal to. So as long as both of the numbers are less than your alpha, you're okay. But if one of the numbers is above your alpha, then you're going to have to fail to reject. Okay. So sometimes that happens that when you go to find your test statistic on here, the exact number you want isn't in there. It's somewhere between two different columns. And then you'll have to use the range, the p-value range there instead of an individual number. Okay. So once you get your test statistic, you'd use table B. For the calculator, you can give it a try. You want test CDF. So when you do, if you choose to use a calculator, you still need to set all this stuff up. So I would just use it to check the numbers at the end. And you'd have to give it the lower t value, the upper t, and your degrees of freedom. So if your calculator does not prompt you like mine did, like put this number in, I wouldn't use it. I would just stick with the table of values. So when you find your test statistic, make sure you draw it. And remember, this guy is not a normal curve. He's a t-distribution. So you're going to use t-distribution degrees of freedom and fill in what is the degrees of freedom. And then you can write your mu there, whatever, wherever your x bar goes, do your shading. Okay, so you can get the information out there. So what I want you to do is I want you to try the check your understanding, and I want you to go check your answer key when you're done. This one, when you get the test statistic, if you're using table B, you're going to have a range for your p-value because it falls somewhere between two numbers, and that's where you're going to go for your p-value at the top. So try it out, check your answers, see how you did. Let me know if you have any questions, and I'll see you in class.